Good day. I'm Nicola John Borci,
And I'm Adrian R. Diwata.
and we're here to talk about the microwave links and the process behind it. Microwaves are a type of electromagnetic radiation, and as are radio waves, ultraviolet radiation, X-rays, and gamma rays. Microwaves have a range of applications, including communications, radar, and perhaps best known by most people, cooking. Electromagnetic radiation is transmitted in waves or particles at different wavelengths and frequencies. The broad range of wavelengths is known as the electromagnetic spectrum, or also known as the EM spectrum. The spectrum is generally divided into 7 regions in order of decreasing wavelength and increasing energy and frequency.
The common designations are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Microwaves fall in the range of the EM spectrum between radio and infrared light. Microwaves have frequencies ranging from about 3 billion cycles per second or 3 gigahertz up to about 30 trillion hertz and wavelengths of about 30 centimeters to 3 millimeters, although these values are not definitive. This region is further divided into a number of bands designated as L, S, C, X, and K. Client. In starting and designing microwave communication systems, details are provided by the client to serve as the primary concerns of the project. Some of the usual concerns are the transmission and receiving locations, the payload, and the cost, though it is usually not limited to those three. These demands serve as guidelines in making the design of the communication systems. Due to the geographical or economical reasons, sometimes compromises must be made in order to achieve what is close to an ideal setup in terms of materials, location, reliability, and economy.
Site selection. Site selection, microwave network design, and analysis of interference are done simultaneously. In most cases, the results are dependent of one another. That means that none of these activities can be done without consultation from the other three.
Several factors should be considered in selecting sites to use, like terrain mapping for possible obstructions such as trees, geographical location for possible line-of-sight path obstruction such as mountains, power sources for antennas, terrain types for possible reflective surfaces such as water or rice paddies, the vicinity of a city or any popular landmarks which could provide obstructions or reflective surfaces, and airports or paths that are commonly used by aircraft.
Some areas are more difficult for microwave links than others, and this is usually related to path or atmospheric conditions. An example of difficult condition for microwave links is connecting offshore such as gas or oil platforms to the mainland. First of all, the platform itself is a continuously moving object, and any radio station would have to be able to cope with the continuous movement of the sea. Second, most areas we would find these platforms, such as the Middle East, North Africa, for example, have a wide temperature range, which means that they are extremely hot during summer days, and with much lower temperatures during the night and winter. This will cause anomalous propagation conditions that can alter and can cause significant phasing. Third, the distances involved are usually long, and there is a limit on the height of metal structures because of safety regulations. The following is a partial list of recommendations for the design and installation of microwave links in difficult areas. In areas with lots of rain, use the lowest frequency band allowed for the project. Consult a local meteorologist station for the real rain data and rely on the crane or ITU rain maps only if no other information is available. Be especially attentive during the design of microwave hubs or in the vicinity of large water surfaces and flat land areas, as they can cause severe multipath fading. Reflections may be avoided by selecting sites that are shielded from the reflective rays. Swamp and rice fields may cause ground reflections, so there is a high probability of multipath fading. The worst time of the year is the rainy season, also called the monsoon season. Hot and humid coastal areas have a high ducting probability. Desert areas may cause ground reflections, but sand does not have a high reflection coefficient. Most critical is the possibility of multipath fading and ducting caused by large temperature variations and/or temperature inversions. Multipath typically occurs at sunrise, sunset, and during the night hours when the air is calm and stable refractive rays form in the atmosphere. Multipath is common during the summer months when the temperature and humidity differences are most extreme. In the North America, multipath outages are most severe near the Gulf of Mexico, the Great Lakes, and the Los Angeles Basin, where humid air mixes with dry continental air masses. Multipath is much less common, for example, in the Rocky Mountain area, where air circulation in the mountains prevent the formation of stable atmosphere. If upfading is a serious problem, smaller antennas, lower transmit power, or receiver attenuators can be used. These changes will improve upfade outage, but can be only used on shorter paths, since this approach will reduce fade margins to combat multipath and rain. If the angle of the path line to horizontal is more than 0.5 degrees, upfading is not significant and can be ignored, since the microwave signal can penetrate the ducting layers that cause upfade. Frequency planning. The objective of frequency planning is to assign frequencies to a network using as few frequencies as possible and in a manner such that the quality and availability of radio link path is minimally affected by interference. The engineers must determine the available frequency bands and channel plans that are specific to the country and the local area in which the network will operate. The following aspects are the basic considerations involved in the assigning of radio frequencies. Determining a frequency band that is suitable for a specific link. Considering path length, site location, terrain topography, and atmospheric effects. Prevention of mutual interference such as interference among radio frequency channels in the actual path. Interference to and from other radio paths, interference to and from satellite communication systems, and so on. Correct selection of frequency band that allows the required transmission capacity while efficiently utilizing the available radio frequency spectrum. Users of a common band of radio frequencies must allow a procedure of radio frequency coordination so as to minimize and control potential interference among systems. It is practical to determine if the planned radio system will experience any interference from the existing environment and vice versa. Potential interference can be calculated for three different cases: interference between microwave stations, interference between microwave stations and Earth stations, interference between microwave stations and geostationary satellite in orbit. Sometimes, an operator may be able to obtain a number of frequency allocations, such as a block, enabling network planning to be performed in advance, without the risk of interference from other users. Most regulatory authorities also operate on a local link length policy, whereby the length of a particular path will determine what frequency bands are available from which the operator may choose. Typically, the shorter the path, the higher the frequency required.
This recommendation provides RF channel arrangements for fixed wireless systems operating in the 7 GHz band. This is used to ensure that the radio frequency spectrum is used efficiently and economically. There are different arrangements with different channel separations to select for your microwave link design. This example is based on the first annex of the ITUR recommendation mentioned. The example shows that the channel separation of 7 MHz is selected with 11 channels. The formula in the recommendation was used to get the low and high band frequency range.
A path profile is a graphical representation of the path traveled by the radio waves between the two ends of a link. The path profile determines the location and height of the antenna at each end of the link, and it ensures that the link is free of obstructions, such as hills, and not subject to propagation losses from radio phenomena, such as multipath reflection. The endpoints of link must have unobstructed radio line of sight. Radio line of sight is not the same as optical line of sight. That is, the ability to see one end of a link from the other. Microwaves have a lower frequency than visible light and therefore behave differently in response to environmental conditions. Radio line of sight requires more clearance than optical line of sight to accommodate the characteristics of microwave signals. An electromagnetic wave does not travel in a straight line. The wave spreads out as it propagates. Also, the individual waves that make up radio signal do not travel at the same phase velocity. A French physicist, Augustin Fresnel, defined the propagation of a radio wave as a three-dimensional elliptical path between the transmitter and receiver. Fresnel divided the path into several zones based on the phase and speed of the propagating waves. The size of each Fresnel zone varies based on the frequency of the radio signal and the length of the path. As frequency decreases, the size of the Fresnel zone increases. As the length of the path increases, the size of the Fresnel zone also increases. A Fresnel zone radius is greatest at the midpoint of the path. Therefore, the midpoint requires the most clearance of any point in the path.
Tomorrow.
Magandang hapon po sa ating mga kaibigan. Nandito po tayo sa NAMRIA at kukunin po natin ang isa sa mga pinaka-importanteng bagay sa paggawa ng microwave systems. Yan. Tara po.
Twenty minutes later.
Tagumpay! Nakuha po natin ngayon ang ating topo map. Ito ba'y gagamitin po natin sa paggawa ng path profiling at siguro po sa susunod na section ng ating video ay ipapakita po natin kung paano gamitin to.
A few moments later.
Magandang hapon po mga kaibigan. Ngayon po at nakabili na po tayo ng topo map. Ipapakita naman po natin kung paano natin gamitin ito. Nandito po ang isa sa mga eksperto sa ganitong mga uri ng sa paggamit ng topomap. Ano po bang pangalan nyo, sir?
Magandang hapon ulit. Ako si Ginoong Adrian Diwata at tuturo ko sa inyo ngayon kung ano ang isang topo map at papakita ko sa inyo kung paano ito ginagamit. Makikita natin sa topo map na ito ang isang parte ng lugar sa Batangas. Makikita natin dito ang pinakamataas na lugar at dito nakasulat ang kanyang elevation. Ngayon, sa topo map na ito, maraming iba't ibang klase ng mga simbolismo na dito natin makikita naman sa legend. Halimbawa, itong mga kulay black na ito dito sa lugar na ito, makikita natin 'yan as isang kalsada, hard surface road. At ang topo map na ito ay isang parte lang ng isang napakalaking lugar na ipapakita natin sa mga susunod pang mga pagtuturo sa inyo.
Napakahusay ho ng pag-explika ng ating kaibigan na si Engineer. Engineer, may tatanong ko lang, magkano ho ba to?
Okay. So ang isang topo map ay nabili niya sa halagang 120 piso. Sa murang halagang iyon, makakabili ka ng isang topo map na malaki ang maitutulong sa ating proyektong gagawin.
Usually po, gaano po karaming topomap ang binibili ng tao sa inyo sa isang araw?
So sa isang araw, ang madalas na naibebenta ng aming departamento na NAMREA, sa isang araw siguro mahigit kumulang mga sa 50 peraso or 100 peraso, depende sa araw at lakas ng mga nabili. Minsan dinibili nila 5 peraso, ganun, minsan 2 lang, minsan 1 lang pang proyekto tulad nito. Ayun, mga ganun karami lang.
Pero madalas po, meron rin mga estudyante na bumibili nito, no? Meron ho ba kayong discount sa mga estudyante na kunwari bibili ng bultuhan?
Discount, wala kaming binibigay na discount kasi sa murang halagang yan na binibigay namin sa ating mga customer, napakalaking discount na yan para sa kanila kasi ito updated to. At yung mga papel na gamit namin dito, syempre hindi naman libre yan, kaya nasa tamang presyo lang.
Ano naman ho ang opinion nyo sa paggamit ng halimbawa ay Google Earth sa paggamit ng kumpara dito at ang Google Earth sa paggamit sa path profiling?
Oo, malaking tulong ang Google Earth, lalo na sa pag-path profiling nito sa proyektong tulad nito. Dahil itong gamit ng topo map para sa mga proyektong ganito, makikita natin as a person dito kung ano yung gamit, kung saan yung lugar na kailangan nating tuntunin, at kung ano yung mga elevation nito na minsan makikita natin sa Google Earth, pero kailangan pa natin ng internet connection at isang laptop. Pero kapag may ganito tayo, andito na sa atin. Kapiling natin yung lugar at makikita natin kung ano yung kailangan nating makita sa mga lugar na to.
At ang pagkakaintindi ko ho ay mas accurate to kung kukumpara sa Google Earth.
Pwede nating masabing accurate sa ibang lugar, pero sa base sa aking nalalaman, mas madalas ina-update ang Google Earth kasi ito, piniprint. Ang Google Earth ay isang software na ina-update lang. Yun lang.
Maraming salamat ho, Engineer. Napakalaki ho ng tulong niyo sa amin.
In this video, I will show you how to do path profiling using Google Earth. Assuming that you have already added a place mark on your locations, the next thing that you will do is to create a path. You can create a path using the path button along the top of the screen. After clicking the button, a window will appear and the cursor will change. You can now click on the first location, then click on the second location. After you do that, a red line will appear. To know the total distance of the path, you can click on the Measurements tab and you will see the distance covered of the path. If you are satisfied with the path that you made, click OK. Once the path is drawn, you can right-click on the name of the path or the line of the path, then select Show Elevation Profile. To measure the path elevation for every kilometer, you have to do it manually. Just hover the mouse on the 0 kilometer mark, then slowly move the mouse till it reaches the first kilometer. The path elevation will be shown just above the graph. Continue doing it until you got every path elevation on every kilometer. It is better to zoom in on the first location to show more precise path elevations. And that's how you path profile in Google Earth.
Equipment selection. The criteria for microwave equipment to be used are as follows. The equipment must be functioning at the chosen frequency the link is to be operated. The receiver should have low sensitivity value, and the transmitter should have a sufficiently high output power. The tower used in the microwave link must possess the following: the capability of the tower to hold loads such as antennas and cables. The ground where the tower is raised should be considered for any ground movement to prevent the tower from swaying, especially in windy environments. Tower height must be enough to avoid tall obstructions. Additionally, towers must be equipped with lightning protection to be able to disperse atmospheric discharge and prevent surge current to enter the equipment, as well as grounding protection.
These are some examples of equipment that will be used in microwave link design. First is the microwave antenna. The gains for the low, mid, and top band are seen on its specification sheet. Its operating frequency is also seen there. Then, we have the microwave radio. In its specification sheet, the transmit power and receiver sensitivity is included. These two are needed in the link budget. Lastly, we have the waveguide. The spec sheet includes the attenuation of the waveguide that will be also used in the link budget. It is very important to choose the equipment that you need for the design because it has a huge effect on the transmission. Now, I will show you the formulas needed in microwave link design. These are the formulas in calculating the total distance, minimum elevation, the earth curvature, ground elevation, and the line of sight. These formulas will be used in getting the Fresnel of the microwave link. Now, this set of formulas are used to determine if frequency can transmit data at a given distance. These are the gains and losses during transmission. In this table is the sample values that was calculated using the formulas that were shown earlier. This is the graphical representation of the link budget. It shows how the gains and losses affect the transmit power during transmission. The blue line is the minimum receiver threshold. It can be found on the specification sheet of a microwave radio. The received signal level should not exceed the minimum receiver threshold because it might cause transmission problems. These are the formulas for different fade margins. The fade margin gives enough gain to accommodate expected fading so that the quality of the microwave is maintained. These are the different formulas in reliability. If the calculated reliability is at 99.99% or greater, the design is theoretically capable of transmitting data without problems.
Link budget. Link engineering begins usually by doing a link budget analysis. A given system has a system gain, that depends on the design of the equipment and the modulation used. The gains from the antenna at each end are added to this gain. The free space loss of the radio signal as it travels over the air is then subtracted from the system. The longer the link, the higher the loss. The energy of microwave radio signals is absorbed by rain. Rain can cause an outage if enough energy is absorbed so that the receiver loses the signal. These calculations result in a fade margin for the link. Anything that affects the radio signal within this margin will be within design considerations. If the margin is exceeded, then the link could go down. The next step is to analyze impediments that could potentially affect the signal. The goal of the design is to get good availability and performance. The results of the microwave network design process will be used during the testing of the microwave system. Microwave path link calculations are performed as a part of detailed microwave system design, and all the detailed hardware requirements and materials are identified based on this information. Microwave design software tools are frequently used for detailed path engineering and interference analysis.
Here are guidelines that could help in planning and some design techniques that will help reduce the potential of having problems later during the application of the design. Using higher frequency bands for shorter hops and lower frequency bands for longer hops. Avoid lower frequency bands in urban areas. Use high-performance antennas in urban areas to minimize interference. Use unprotected systems only for spur sites, low capacity, and or general low importance links. Use protected systems for all important and or high capacity links, leaving up space for capacity for future expansion of the system. Below 10 GHz, multipath outage increases rapidly with path length. Multipath effects can be reduced with higher fade margins. If the path has excessive multipath outage, the performance may be improved by using one of the diversity methods. The reflection coefficient decreases with frequency.
Vertical polarization is less susceptible to rain attenuation. Space diversity is a very expensive way of improving the performance of the microwave link, and it should be used carefully and as a last resort. The activities of microwave path planning and frequency planning preferably should be performed in parallel with line-of-sight activities and other network design activities for best efficiency. In addition, start the official process of frequency coordination and licensing process as soon as possible. Use updated maps that are not more than a year old. Magnetic inclination as well as the terrain itself can change drastically in a very short period of time. Make sure that everyone on the project is using the same maps, datum, and coordinate systems. The datum or reference ellipsoid selection must be the same for the site data, image, and elevation files. The same map projection must be used for the image and elevation files. Consider future expansions in the frequency planning activity. It must be possible and easy to add new hops as the network expands. Perform detailed path surveys on all the microwave hops. Maps are only used for initial planning as a first approximation.
Keep in mind during the path surveys that trees and other vegetation grow, and plan for at least 10-year growth, preferably even 20 years. If trees are already matured, their rate of growth is lower than the young trees. There are very few areas where trees will grow over 100 feet. Obtain microwave radio, transmission lines, antennas, and so forth only from a reputable and reliable supplier. Of course, this would only matter at the application phase of the project. Keep a good record of all the design documentation and all related and relevant papers. Finally, Do not try to overdimension the network, as this will make it unnecessarily costly. Every network, regardless of the type, will have brief outages from time to time, and microwave networks are no exception. A network that does not fail is a fiction.
At dito nagtatapos ang aming proyekto. Maraming salamat po.
Okay na to, Borci.
Good afternoon, everybody. I'm Nicolai John Borci.
Public yun.
Sige,
Sabi ko tuloy-tuloy.
Tuloy.
Good afternoon, everybody. My name is Nicolai John Borci,
And I'm Adrian R. Diwata.
and we're here to talk about
Microwave link. Title?
microwave links.
we're here to talk about microwave links.
Microwave. Microwave?
How to design. We're here to talk about how to design a microwave links.
To design microwave link.
Pwede bang i-type yun lang?
Hindi, huwag na. Sige, type natin.
Parang hindi ko makakalimutan. If upfading is a serious problem, smaller antennas, lower transmit power or receiver attenuation. Blah. Sabi ko tagumpay. Meron akong mabait na nilalang na nag-send sa amin ng mga tips and tricks sa paggawa ng microwave system. Hot and humid coastal areas have a high ducting probability.